Okay. Okay, so I'm going to talk about the summer process study. Armin mentioned the winter process study, which was the colder outbreaks. This is kind of the parallel for the summer. So thanks for the folks that have contributed data and contributions to this. I'm going to cover a couple of different things. We've got a paper that's coming out pretty soon summarizing these 6 process study flights. I'm going to cover a little bit of that in this talk, but I've also got a poster that's got more of that paper. Some ongoing works on the mechanisms for cloud aggregation, and then some fairly recent and new ongoing work related to cloud remote sensing. And John Hare's got a poster that has some more of the background for some of that. Okay, just a quick recap. So the idea for the summer process study spawned off of kind of seeing pictures like this in the summer in our region. Quite often you see these kind of clusters of clouds, and along with that, those clusters of clouds, you see kind of variability at the mesoscale in the water vapor field. So we wanted to look at why that happens and what causes the cloud to kind of aggregate in this way. And then kind of as a second question to that is, why does this type of thing happen where you've got regions that are kind of coexisting, where you've got very different morphologies in the cloud? You can have this kind of uniform cumulus in the A region and then kind of more clustered in the B region. They can both be in the same area. So to kind of inspire, sorry, I've got a little box here that's in my way. To kind of inspire thinking about this in the literature, there's kind of maybe 2 competing or conflicting kind of arguments for why this might kind of happen. The first is not requiring precipitation or any kind of heterogeneity in the radiation or surface flux fields, and it's just something that's kind of like internal to the system. The clouds themselves will tend to cause this aggregation to happen. And then the second is that precipitation is kind of a necessary component to this. You need to have the cold pools forming, and that kind of like causes the scale growth. Oh, sorry, my technical difficulties. Okay, yeah, and so as motivation for why we want to do this is that kind of understanding the cloud morphology is important to understanding cloud radiative effects, both in present climate and in future climate. Okay, so what did we do? We designed a module that summarized on the left. The King Air flies at its standard 9-kilometer altitude over the region of interest, and the Falcon performs this kind of step maneuver down through the cloud, covering multiple altitudes in the cloud, and then below the cloud, and then moves off away from where the cloud cluster is and performs a spiral in one of the kind of clear areas off to the side. In plan, uh, you can kind of see how that's laid out. The King Air does this wheel and spoke pattern, so multiple transects, and then drops drop-ons on the perimeter. We did 6 of these. 3 of them were near the coast during the first 2 years of Activate, and then during the Bermuda deployment, we did a further 3 out in the area near Bermuda. And it turns out that the conditions that are typical for these kind of this kind of cloud organization all seems to have similar meteorology. At least the cases that we flew were all very similar in their meteorology. The subtropical high was kind of located off to the east, and the trajectories for all 6 cases were basically from the central tropical Atlantic wrapping around the southwest side of the high. This is a satellite view of the 6 cases. So as I mentioned, the first 3 are over the Gulf Stream near the coast, and the second 3 are out near Bermuda. Nature obviously gives us what we get. It was not quite exactly what we had kind of hoped for, but this is what we ended up with. Each of the cases are slightly different in their cloud morphology. So you can kind of see that. I've shown here on the pink, I want to just highlight what that is. That's the track of the cloud cluster. So here you're looking at the center point of the module, and the pink line basically shows how the clouds basically evolved in time. Quick worth mentioning is on cases 4 and 5, we actually did 2 modules in case 2 full modules in the case 5, and in case 4, the Falcon had time to do a second round of cloud sampling just to the south. So they're 4A and 4B, 5A and 5B. Okay, to just touch on that cloud tracking a little bit more. So this is from case 3. So again, similar image from the previous slide on the left, using sequential satellite images, we can kind of track through correlation the movement of the cloud cluster and then relate that to the vertical wind profile. So that's what's shown in the hodograph, basically showing what the wind looks like with height and then the motion of the cloud itself. That's the square. And we can reframe our coordinate system in a cloud-centric coordinate system. And then that's the image on the right, or the video on the right, is basically showing what that looks like. And I found that quite useful in order to look at the cloud evolution, because it takes away the kind of broad advection of the cloud. And you can kind of see how the scene is evolving relative to the cloud cluster. Okay, I'm going to talk a little bit about precipitation, and since that was one of the kind of leading hypotheses for what's happening here. Summary of all the precipitation measurements for all 6 cases, and there are some caveats about this based on using the in situ data. We didn't have the benefit of radar, so we had to kind of do our best to try and understand what the coverage of precipitation was for each of the cases. Essentially, the take-home message is the comparison between the 6 and case 4 and case 6, which were 2 of the Bermuda cases. They were the ones where I believe precipitation was significant in respect to the dynamics of the cluster, whereas in other cases it was really kind of a secondary an effect rather than a cause. Another thing I want to highlight from case 6 that was quite interesting was during our minimum altitude sampling of case 6, we saw 3 different flavors of precipitation influence on the mixed layer. So basically just 3 different locations sampling underneath the cloud and saw 3 very distinctly different responses to that precipitation. The first one, you couldn't call it a cold pool because it's not cold. It's actually neutrally buoyant with respect to its surroundings, but it's bringing dry air down from aloft. The middle one is kind of their typical cold pool situation you'd expect from deeper clouds, where you're bringing in, again, bringing low theta E air down, but in this case, it's actually evaporating more of the rainwater, so you're actually getting the cold anomaly. And then on the right is the kind of boundary layer evaporation effect, where you're seeing basically boundary layer air that's been influenced by precipitation. So all 3 seem to happen in the same location. So I thought that was pretty interesting. And we can kind of summarize what that does to each of the cases by looking for these same signatures. And in fact, only case 2, 4, and 6 showed any signature at all of subcloud precipitation influence on the mixed layer properties. This is another example related to precipitation that I thought was pretty interesting from case 3. So while we didn't see any influence below the cloud in case 3, there was actually ample rainwater quite high up in the cloud. And when we flew through the cloud 4 different times between 2 and 3 kilometers, we saw this consistent pattern in where the rainwater was located compared to where the core of the cloud was located. So on the left, the red indicates updraft air that basically has very little rainwater, surrounded by downdraft air that has quite high rainwater. And so what's happening here, I think, is that one of the factors in producing rain, obviously we need time to produce collisions, but time also destroys buoyancy. And so this rainwater is being injected to the side and is evaporating into the environment and not actually contributing to precipitation at the surface. So our second kind of hypothesis about what's happening here is this mesoscale overturning circulation, or internal cumulus response to aggregation. And so we can use the dropzone measurements. I'll just hop back quickly to that. So we had the dropzones in the environment surrounding the cloud cluster in each case. We can use them and basically calculate an effective mesoscale vertical velocity profile. And when you do this, there's quite a lot of mess in this plot here, but if you highlight the ones which had that precipitation dominance to them, they have a distinctly different vertical profile of mesoscale velocity. So again, I thought that was quite an interesting finding in respect to the link between precipitation and the mesoscale vertical velocity. I'm going to go through this very fast, but this is basically just a quick overview of this Bretherton and Blossy uh, paper. So the idea is that if you have kind of uniform amounts of convective mixing and then you perturb that, the environment responds basically by creating a circulation. If that causes drying, then you'll revert back to something that's uniform. If it causes moistening, then it will basically strengthen the circulation. And they find that if you strip out all the physics and basically just have the internal dynamics of the cumulus, what you need in order for that to happen is this convex relationship between theta V and theta E. And when you look at our dropzone data, I mean, you could make the argument that maybe we kind of see that, but I think in reality, you probably see it in all summertime conditions where you've got conditionally unstable air. And indeed, if we look at all of the Activate data in this way, we can see that our summer process studies actually sat off kind of to the top right, where this convex relationship is happening, but equally it happens really in all of the summertime data. But we don't necessarily see this organization pattern happening in other cases. Wanted to make a quick mention of this paper, recently paper, basically saying that you can see this in, at least in modeling, you can see this everywhere. It's always unstable to this length scale growth. Okay, I'm going to skip talking about this too much because this is basically the poster, but I wanted to highlight that these measurements that we made were really rich in terms of the vertical information that we got. Case 6, we actually got 20 levels in the cloud. So there's a lot of amazing data there to be used for understanding vertical variability in cumulus clouds. Okay, just to wrap up, I'm going to touch on some of the things we're looking at with cloud remote sensing. This is work with John and also with the RSP team. So we want to try and use LiDAR ratio to help with understanding drop size. On the left, this is a paper from 2021, basically using Calypso comparisons to MODIS, looking at the LiDAR ratio versus effective radius. And we'd expect from theory that as effective radius increases, LiDAR ratio should go down. And indeed, you see that in the data set. One thing that's kind of interesting is that that Calypso and indeed our data as well seems to be more sensitive to changes in size than theory would predict. There's actually more dynamic range in the LiDAR ratio than theory would predict. So what I've done is I've taken this relationship on the right, which is just for the process study data, and applied it to the HSRL LiDAR ratio to give an effective radius. And then if I compare that with the in situ effective radius, that's shown on the bottom. And I think this was pretty amazing comparison, to be honest, especially that it captures some of the detailed structure, like in case 6, some of the structural variability in the effective radius with altitude. So this was really encouraging. So I took this and kind of looked into it a little bit more in terms of trying to use this as a proxy for identifying precipitation. So here's 2 transects from case 4, which is one of our precipitating cases. And where you have regions of low LiDAR ratio, so high effective radius, those correlate with the regions where you have higher cloud top, more of a convective structure. And if you match it up with where we saw in situ subcloud rain rates, see if I can point to that down here. The red regions are where you've got a LiDAR indication of rain, and the gold colors represent the Falcon rain rates. So I think that was a pretty exciting comparison there. Lastly, case 6 was pretty unique in the sense that we actually captured almost the full life cycle of the cloud cluster. And so repeated passes over the cloud allowed us to actually characterize the evolution of the cloud with time in terms of the maximum height and also the shape of the cloud. So these four these pink points here plus this circle there transects across the axis of the cloud, and this is showing what that looks like in terms of the height cross section. You can see with time the cloud evolves from something that's fairly symmetric about its axis to something where you have increasing PBL cloud on the southeast side and decreasing cloud on the north side. So it kind of evolves from something like this kind of symmetric shape, to something that has a clear inflow region, and then this kind of detrained stratiform region is kind of off to the side here. Over. Last thing to talk about is ice. We didn't have ice in any of the cases other than case 6. The Falcon didn't see it just as a result of starting before the cloud grew to the point where it formed ice. The LiDAR ratio is also useful for identifying ice. Once the LiDAR ratio is above about 25, that's not physically explainable by liquid drops. And so here, where we see indications of ice formation, it coincides with the highest part of the cloud. And so again, we're working on this, trying to get cases where we have in situ comparisons, but definitely an exciting potential use of LiDAR ratio to identify ice for the Activate data set. Okay, I just want to wrap up with this. I'll let you read the text, but basically this is our working hypothesis for how I think that these cloud clusters are operating. Essentially, the ones that are on the left more or less conform with the conceptual idea of the Bretherton and Blossy paper. And then once the clouds develop a little bit, one of the things that seems to be necessary is this asymmetry that forms, basically creating kind of a sloped updraft, and that basically ends up being the demise of the cloud cluster. So that's all I got.
Ewan, it's really exciting to see these results. And just by the way, International GeoX program is emphasizing the mesoscale aggregation of channel convection. So exciting area. My question is, do you have any analysis or conclusions in terms of the specific shapes or distributions of those channel clouds? For example, now people are talking about the popcorn type clouds and cauliflower type clouds. Any insights on the conditions leading to different shapes of clouds?
Yeah, so one of the things that trying to take our region and the environmental conditions and relating it to particularly this Bretherton and Blossy modeling paper, which was under a had an inversion. So it was kind of, it was a boundary layer paper basically. There was no vertical development of the clouds once they aggregated past where the inversion was. In our instance, there really was no inversion in any of these cases. There was no the environment was capable of actually of having deep convection. In fact, there was deep convection within the region, and so these clouds had no capping limit on their vertical extent. So in terms of the morphology of the clouds we ended up flying, I think that yeah, it's really just it was more of a aggregation from the point of view of a deepening mechanism or a transition to deep convection, or at least to congestus. So I don't know if that answers the question of how you would describe the clouds. I think that for the most part, these were typical marine cumuliform clouds. There was some layer clouds that happened in the precipitating cases, but the non-precipitating cases didn't really have any of that. It was just cumulus that was just getting thicker and deeper. So I don't even know if that's a good answer to the question, but yeah.
Thanks. Yeah, I was going to ask, well, a couple of things. First of all, you got these like little wispy clouds there. Do you think they're detrained layers later? I mean, we talked about this veil cloud stuff in the Northeast Pacific stuff.
Right.
I'm curious about that. Yeah.
Yeah. So it's I think these are altocumulus detrained clouds. They are thin, but in some cases they're not. I don't think you would categorize them in the same way as the veil clouds. This is maybe a good way of looking at it. So I think this is the area on the right that's labeled stratiform. That had a distinctly different appearance to it, but you can see that at least in parts of it that it's the extinction is fairly high, and in fact the region basically under where it says stratiform in the top plot, that's attenuating only about 50 meters into the cloud. So it's not like it's less than an optical depth or something like that, right? These are thick opaque clouds basically, but there are places where it thins out. In terms of the mechanism, I don't know whether it's directly a result of just kind of the residual of the cloud, the parent cloud itself, or whether these are being formed by gravity waves or any other kind of mechanism. But I don't think it has a single category like like that. Yeah.
Thank you, Ewan. This is really amazing. So we have done basically all the summer cases area simulation, but majority of them are really difficult to capture the vertical extent of the clouds and the cloud morphology using the idealized LES. And so my question is that you really nicely show some possible explanation for the mechanism of driving these shallow convective clouds. So what are the main mechanisms do you think that could drive this, the morphology of these shallow convective clouds for these cases that you showed here?
So I think that even though we had a really good coverage of dropsons in all except case 6, at least 12 dropsons per case, I found it's pretty hard to actually capture this mesoscale vertical velocity. It's pretty noisy, and we were only covering about 100 kilometers of area of horizontal scale, which is about half of the horizontal scale that the circle thing, it's also in the idea behind doing the circles to capture the large scale divergence. The idea there is that your large scale divergence field for this is larger than the scale of the circle, at least above the boundary layer if you're using it for that. Here we've got this cluster, and then like 200 kilometers away we've got something else going on. We've got deep convection elsewhere. Like there's so much stuff going on that I don't think you can actually say that the response of this cloud cluster is measured by just looking at the environment around it. So I think that's a challenge for what we've done here. But yeah, in terms of being able to explain the mechanism, I think there is a clear shift once precipitation goes above a certain rate. It then takes over the dynamics, and I think that this tilted part is an important piece to that, and it kind of just pinches off, and then it can't feed itself anymore, and then it's toast. So